Okay.
So, and one last announcement before I turn things over to Shawn. Just a reminder for everybody's here that in November, we do not have an ECSS symposium. That's one of the 2 months that we take off. We skip November due to conflicts with supercomputing. And with that, Shawn, go ahead and take it away.
Okay, great. Yeah, do warn me, Bob. I don't seem to be able to keep the chat window up on my screen for some reason.
Yep, I'll be monitoring.
Great, thank you. So thanks everybody for letting me come and present to you. My name is Shawn Brown. I'm the director at the Pittsburgh Supercomputing Center. And the Pittsburgh Supercomputing Center is a joint research, computational research facility between Carnegie Mellon and the University of Pittsburgh. And I have had the fortune since about for about a year now being the director there. I came from McGill University in Montreal, where I worked in neuroinformatics, data sharing platforms. And I have recently taken over as the PI and project director of the Bridges 2 project. So I'm coming here to talk to you today about our latest general purpose platform, Bridges 2. And we're really excited about this. It's a really cool machine. So thank you for letting me come and talk to you guys about it. So Bridges 2 was an award from the NSF. It was part of the machine granting awards from SIZE. I'm sorry, from OCE, excuse me. So we were awarded the grant in last year, and we're working to deploy the system. The official title's there if you really want to see it. And I just want to note that we're working very closely with our partner Hewlett Packard Enterprise, who is building and delivering Bridges 2 as well. So we really, first off, thank the NSF for their generous support and Hewlett Packard for their being such a great partner to get this machine up and running. So I just put this up for first off, and I'll leave you with this at the end of the presentation. This is just a list of places where you can go to find out information about Bridges 2. So we have our Bridges 2 website at that address. That's where you can go to find out more about the machine, get all the latest news, get updated timelines. We have an early user program, which I'll tell you a little bit about towards the end, where you can apply at that web address for the early user program. We're asking people that want to have software and data to be housed on the Bridges 2. So the platform is uniquely designed to, sorry for that jangling, my dog has decided to fervently scratch himself right in the middle of my presentation. So if you have a special software that you want to implement on the machine, or you have data, we'll actually house open data sets for data analytics and research on there. You can go to those websites there and fill out a form, and we can that will help inform us on what we need to put on the machine, as well as what data we can house there. All of our requests, allocation requests, we're a strong partner with Ecss, and so if you would like to ask for time on Bridges 2 or join the early user program, you'll be doing so at the Ecss portal. And if you have any other further questions, please just email us at bridges2@psc.edu, and we'll get back to you as soon as we can. So one of the motivations for us to build Bridges 2 is rapidly evolving science and engineering. So the landscape of high performance computing and computational research has changed drastically over the last decade. I've been in the game for about 25 years, and it's changed so rapidly over the 25 years that I've been in high performance computing. We really wanted to build a machine that really supported the new ways of doing computational science, not necessarily just only traditional computational science. And that included things like, the high performance and high throughput computing simulation and modeling, AI and high performance AI, not just regular, AI is pervasive around computational research, but we also wanted to take AI to the next level and have machine learning and deep learning that could be scalable and larger than we could do, could be done in the past. And you'll find out a little bit more about another system that we're going to be deploying at the PSC called Neocortex, which is, I would say, extreme scalability in AI and machine learning and deep learning, which is a really exciting system. Sergio will tell you a little bit about that after my talk. We really want to service the community and make a machine that is available for data analytics and data. The name of the game today is not necessarily having the most iron, but really having the most data in a sane and rational place ready for machine learning, ready for processing, having portals and web access to that data so that we can actually perform computational science and make complex workflows and complex computational methodology with this data. And so one of the things that we wanted to do with Bridges 2 is make sure that we are a data-friendly platform and are able to bring that data there and make it and work with other people to bring data in and have proper metadata to be able to feed our algorithms in a way that hasn't been done before. Definitely easy to use, familiar software, interactivity, productivity. We're not just going to be supporting the command line. We want to be able to support all sorts of modes of computation to make this as applicable to the community as possible, so that we reduce the barriers to people using high performance computing for their research. Rather than us training them to use the way that we do things, we want to try to enable them to do their research in their own particular idiom. And then finally, work interoperability with all sorts of different types of things, including, workflow engines, heterogeneous computing, cloud resources. We want this thing to be a member of the ecosystem, not just a standalone machine, but really a resource that's widely available and applicable to a number of different rapidly evolving research paradigms. So we started this journey a long time ago with Bridges, and many of you have probably used Bridges or know about Bridges. Bridges, the idea behind Bridges was, to build a machine that was a heterogeneous computing platform that really pioneered the idea of bringing new communities to high performance computing, especially in the AI and big data space, where we evolved the machine to being able to support new types of computing in those arenas. We expanded the machine to add Bridges AI, which added some GPU capability that was never before available to the research community. And we made this machine with the explicit purpose of finding new communities and bringing them to the computational research area. We were pretty successful with that. We had over 2,100 projects, 16,000 users, which was a leap for us, and it was an awesome leap. We really enjoyed interacting with the research community through this research and with our partners as well. 800 institutions, a number of different fields of study, and we also really pushed education allocation. So using this machine for training and education as well was a big factor for us. So Bridges 2 is, while it is a new machine with some really exciting innovations, it's a riff on that concept. We want to now, instead of just supporting non-traditional computing, we want to support rapidly evolving research. So converged collaboration with data, highly multidisciplinary science, highly scalable AI and big data research. So we built this machine as a follow-on in this concept for us. So it's about 3 times larger than Bridges, although capacity isn't really what we were going for. We're trying to make a machine that really supports the new rapidly evolving research community. Faster computing. We have the latest AMD EPYC processors in here. I'll tell you a little bit more about that. We've designed a file system that has a tiered data management with some really fast access and fast flash array. Smarter science, designed it for full system AI and data-centric computing rather than just being it's still applicable for traditional computing, and we don't want to leave that community behind, but we also want to try to take all of the community to a different level when it comes to being able to access data and complexity in their scientific research. And of course, scalability and making it interoperable with as number of different systems as we can as possible. So the application areas that we look to support these are just an example. We really believe that Bridges 2 is going to be a catalyst for a lot of new paradigms in research and multidisciplinary research development. But some examples of scientific areas that we want to support, for instance, gene expression, advanced digital pathology with AI. So being able to take large collections of images and being able to perform rapidly AI and machine learning on them so that we can look at being able to help researcher or help medical profession be able to find and diagnose different pathologies in cancer and other diseases. mapping the human body at the cellular resolution. So we have another project that we're working on here from the NIH called HubMap, which is actually creating a repository of highly structured data of the human body at the cellular resolution, all of the organs in the human body, and being able to leverage that and leverage data sets like that, and whether it be in neuroimaging, medical science, or any other type of field, having really well curated data collections to be able to put through and do complex workflows, AI, machine learning on them. That's really what we designed this machine for. Developing smart cities, so geographic data as well, simulation modeling and agent-based modeling, the type that I do in my research, being able to create large complex models to be able to look at things like how do we design better cities, how do we design cities, for instance, to optimize health outcomes for like obesity or good food environments, things like workflow from the Large Hadron Collider, improving storm prediction, understanding immunity, obviously a topic that's kind of relevant nowadays with our COVID pandemic, and also designing new materials. And let me just say, this is just an example of the types of areas of research that we can support with Bridges 2. Really, the door is open to a wide array of new areas, and what we're really targeting is areas like AI, machine learning, and like simulation modeling that bring together a large collection of multidisciplinary researchers under one roof to be able to create new paradigms of research. That's really what we're targeting with this machine. So just a high-level architecture of Bridges 2. So we have a number of service nodes that connect to the ones that are listed here in orange. So web server nodes, database nodes, data transfer nodes, login nodes. These are the ones that people will interact with. They're all connected by the same interconnect, which is a HDR, Mellanox, and InfiniBand network. We have our, in yellow here, you have our file the data file system part of the architecture, which has a tape archive. So we have far line, near line storage, as well as a flash array for very fast and quick access to data. We have our management nodes in red there. Those are the ones that will help us to maintain the machine. And then the compute nodes, which is the iron behind the fire of Bridges 2. We have a number of different ones. I'll go into detail about which ones, what all of those are, but we have a collection of heterogeneous nodes to suit everyone's needs. And the idea being that we want to create platforms on top of Bridges 2 that allow people to find, navigate, and utilize all of these resources together to solve their complex research problems. So, as I was saying before, Bridges 2 really builds on the flexibility of the architecture of Bridges and innovates in ways to, help to support rapidly evolving, computationally intensive, and data-intensive research, and really make it a platform where we can build other platforms on top of to really foster convergent collaboration and convergent research. So whereas Bridges was really about supporting non-traditional computing, we want to move with Bridges 2 to the next level. So core concepts with Bridges 2 are obviously converged high-performance computing, AI, and data. So under one platform, it's not just enough to be able to do AI and machine learning and have like some virtual machine or some set of GPUs do that. We want to put all under one roof, the data architecture, the high performance computing, the AI, all together under one roof, so you can build a platform to really do highly convergent AI machine learning, as well as other types of simulation modeling. It's designed with a close topology optimized for data-centric computing. So it's the network is very well designed to be able to move data to where you need it to go and be able to compute on it fast and then get data back out of it in a way that allows you to do this in an optimized fashion. Heterogeneous workflows and heterogeneous node architecture. We have, whatever you need. CPUs, we have large memory CPUs. We also have AI targeted GPUs, really heavy GPU component to this. And not just a GPU component, I'll talk about it in a little bit, but these are really highly capable GPU nodes that we have on this machine, as well as we'll be moving over the hardware that we had in Bridges from Bridges AI over to Bridges 2. So that will also be accessible for highly scalable AI research. And flexible software environment, so we're designing it from the ground up using containers and technologies like SPAC that allow people to define their software environment in a very flexible way, as well as being able to put data collections on there, but also be able to build platforms like web-based platforms or workflow architectures or complexity science platforms over top of Bridges. So having a really good service-oriented architecture on top of this. So some innovations that Bridges 2 has beyond Bridges are the new CPUs, which our friends at SDSC are also putting in Expanse. These are the latest and greatest AMD EPYC 7742 processors. We'll have 128 cores per RM node. Really high level of AI scaling. We'll have 192 V100 32 gigabyte GPUs. They'll be also have an architecture of NVLink, so they'll be directly connected to each other within the nodes, as well as being connected through the high-speed network together. A flash array drive, which is going to be a little bit larger than 100 terabytes of usable, but this will be really efficient for large collections of small files where you have a lot of metadata transfers, as well as being great for other file transfers. And then that being connected to our nearline and farline storage in a tiered way. Our interconnect is awesome. So it's a Mellanox HDR 200 InfiniBand. We'll be able to support all the greats like MPI, OpenMP, all those. Well, OpenMP obviously on the nodes, but all the distributed parallel. But we also will be able to support all the new like RDMA architectures, GPU Direct. It's just a really good connect, and it's all connected together under one interconnect. Our farline or nearline storage, Cray cluster store, is a highly efficient parallel file system, and we also will have the HP DMF data movement framework that gives us a single namespace, so you won't even know whether you're on the tape, you're on the cluster store. It will be completely transparent to the users. So with the machine, of course, we will support all the people that want to log in and use the command line, like me. I like to use the command line, but we also want to, support the new ways of interacting with computational infrastructure. So it's not just enough to have the command line. It's also something where we want to support and promote interactivity and things like Jupyter notebooks, being able to support MATLAB, using Open On Demand to be able to pop up Jupyter hubs and Jupyter notebooks, using containers to be able to support easy transfer of different types of programs, like with Singularity containers. So we're going to support all of these things, and not only support them, we want them to be the primary mode of the way that people will interact with this, with our Bridges 2 architecture. So you can see a litany of different things, and of course, supporting all of the different frameworks for AI and machine learning, which are out there, as well as R and Anaconda. So we really want this to be, to move beyond just traditional computational research, but also going into the interactive, new ways of doing things so that people can interact with it however they wish to get their research done. So really removing the barriers for people to do new and exciting ways to do computational research. So just a little bit about the different nodes of Bridges 2. So we have 4 different types of nodes. 2 of them that I'm going to tell you about here are the regular memory nodes, which we call RM nodes, and the large memory nodes, LM nodes, really uniquely named. They provide the general purpose computing and AI inferencing for Bridges 2. So each RM node is going to contain 2 AMD EPYC Rome 7742 CPUs. So they'll have 64 cores each. So it'll be 128 cores per node. You'll be able to do up to 256 threads in each of the nodes, with the 2.25 gigahertz, but it could go up to 3.4 gigahertz depending on how the workload on the machine or on the node. We'll have 488 of these RM nodes with 256 gigabytes of RAM, shared RAM. Those will be the RM nodes, and then 16 that will have 512 gigabytes of shared RAM. Those will be the LM nodes, DDR4 3200 memory. And then each of them will also have about a 4 terabyte NVMe SSD drive, and they're all going to be connected through the HDR InfiniBand. So these will be pretty beefy general purpose nodes that people will be able to use for all sorts of different types of computing. And we have a lot of those available. And then the next level is the extreme memory nodes. These will be for people that need, beyond the normal level of memory usage. We had in Bridges, we had up to, I think, 12 terabyte nodes of this kind. We're going to have on this one, they'll all have 4 terabytes of RAM. They will be Cascade Lake based, 24, they'll be 96 cores, 96 cores each. I got to do math in my head quickly. For each of those each of the nodes, and those will each have 8 terabytes of SSD memory. So these will be good for things like genome sequence assembly, graph analytics, or if you have a really large database that you want to move into memory and run on and do a lot of processing on, these will be your nodes. So we'll have I believe we'll have 16 of these available. I don't know why I didn't put, no, we'll have, 16 of these available in the architecture. And then finally, the GPU nodes, these are not going to be the only GPU resource we'll have on here. We'll also be moving over things from Bridges AI, which will have a DGX2 and some other nodes that will be available from the Bridges. But these are going to be, each of these nodes will be, have NVIDIA, 8 NVIDIA Tesla V100 32 gigabyte processors or cards, which are the really high level or high end GPUs. They'll also be linked up together through a direct interconnect from NVIDIA. They'll each have Cascade Lake CPUs, 2 of the CPUs in it, and then 512 gigabytes of RAM available to you through there with another 8 terabytes of SSD, and they will have 2 channels to the interconnect for the HDR InfiniBand. So as we said, heterogeneous, different types of nodes depending on what kind of work you want to do, but these will be, all of the nodes are very capable and very have a different purpose. And we're really excited about all the capability we're going to be able to provide in Bridges 2. So the Bridges 2 GPU infrastructure will be connected through all of the HDR InfiniBand and the spline switches. So they'll be just as they'll actually be more connected, and they'll be faster, have a faster connect to all of the architecture of Bridges 2, and it also support a remote direct memory access communication between the GPUs without having to go through the CPUs. So that's going to greatly enable how you can scale these the use of the GPUs up on this. So we'll be able to do large, really scalable AI as well as GPU accelerated simulation modeling as well. So this is a really high level capability, and it allows us not only to do AI on one of the nodes, but also allows us to do AI over the whole scalable architecture. So whether you're doing, you want to use one GPU, you want to use just 8 GPUs on the node, or if you want to use all of the GPUs, we'll have a very scalable architecture to allow you to do that. And just a little bit about our data infrastructure. So the data infrastructure is managed by HP's data management framework, which is allows us a single namespace with a user-friendly rule-based migration. So you won't have to be cognizant of where your data is going throughout the ecosystem, but it'll be in there where it needs to be in order to use it in as quickly as possible. So the cluster store comprises of a Lustre file system, which will have 15 petabytes of usable space, 129 gigabytes per second read, 142 gigabyte per second write. And it will be allocated through the Ecss process. We'll also have this flash array that will be available for really fast access for really high metadata needs as well. So that will be over 100 terabytes of storage. That can do 9 million IOPS per second, which is pretty nice. This is really good. I mean, we used to have a lot of problems with our neuroscience data sets because they had a lot of little files and only like one big file. So this would be excellent for that kind of processing. And then we'll also have a tape library that will allow us to offline storage that's not being, or data that's not being used regularly, but still keep it in a way that will be able to be accessed in later. So we can archive things. We can also house very large data sets there for people that need to use parts of them and things like that. So a really interesting tiered approach to the data storage for Bridges 2, really to facilitate and catalyze data analytics. So, one thing that I want to talk about the AI capability a little bit, because it is really one of the things that we really designed the machine to do. And as most of you know, the AI results have been growing and growing just rapidly over time, to the point that we're getting into a point where we need, petaflops per second per day of just computing to keep up with it. And this is just a chart from and they had the 2019 annual report of AI, where it's showing that it's doubling. The need for AI processing power is doubling basically every 3.4 months. So it's kind of a new Moore's law approach to having to get more and more capability available for AI and machine learning. And on top of that, our networks that we're using for AI and deep learning are getting bigger and bigger. The data sets are, it's being driven by having so much larger data sets, as well as having more complex problems that we want to solve with the deep learning models and the machine learning models. And so we're getting to a point where we really need highly scalable AI architectures. But with that comes complexity. And we also have to make sure that when we build these machines, it's not just about putting iron down, it's about making sure that the common frameworks and data and software and platforms are available to the researchers to be able to do the highly complex research. So with Bridges 2, we're really focused on 3 areas there: productivity, usability, and interoperability. So in the productivity side, we're building the architecture. So I've outlined, the data, or the architecture itself, the hard iron that we've put down for Bridges 2. And the idea being that we have this heterogeneous supercomputer that gives you all this data capability, all this traditional computing capability, and highly scalable AI capability. And we want to make that really sort of an AI engine or a computational research engine that people see as the platform itself interacting with a number of different types of platforms, and make that a highly productive environment for people to be able to scale up their architectures. And then make sure that we're supporting all sorts of different, all the popular ways of doing computing, including all the AI architectures, but also things like Jupyter notebooks, which is what the kids really love today, using Jupyter notebooks and Jupyter Hub, and providing that through different architectures like RStudio and Open on Demand, where people can interact with the computing in a way that's not so complex that they get lost in the data and lost in the computing that they need to do. And then really making Bridges 2 a part of an ecosystem. So we don't view Bridges 2 as something that is just a standalone. It's not possible anymore to think of our machines as a standalone computing platform that you just go to Bridges 2 and that's all you do. We need this to interoperate with the rest of the computational research ecosystem. So we're working really closely with our partners at the University of Pittsburgh and Carnegie Mellon to help us to integrate this with their cloud resources, as well as integrating it with things like AWS and other cloud resources, to be able to smoothly work in the environment that you want to do, and be able to move data and computation in and out of this resource as seamlessly and barrier-free as possible, as well as leveraging some of the projects that we're doing to learn more about how do we provide data architectures like big collections of data of human imaging, genomics, and cellular data, and like in HubMap, or BILL, which is the brain imaging library, which is a large collection of animal brain data, and working also with a lot of other partners to be able to figure out how do we put this data in a same place be able to move it in and really catalyze big data analytic processes with this machine. I don't like to call it a machine. I just said machine, but really it's a platform, and we want to view it as a platform for doing research. And that's really sort of how we view the system, rather than just being a machine, because that's not really what we're into nowadays. So the early user program, we don't unfortunately have a date for the early user program yet. We're still solidifying the deployment schedule for Bridges 2, but I just want to let you know that you can apply for the early user program. It will be a time about a 30-day, at least a 30-day window where you'll be able to, at no cost and no allocation, be able to log in and scale up your codes, tune, optimize your software, as well as run some science. So we really want to see the purpose of this machine is not to get the biggest flops. The purpose of this machine is to produce as much science as we can with it. And so really our metric is get on there and do some great science free of charge, and help us to be able to shake down the machine, but also help us to get the software and the environment that's going to help you to do your research in the future available on there, because that's really what our goal is to produce as much good scientific research as possible. The only thing that we'll be asking from the early user period is, first off, applying for it, which you can go to the website and find out how you apply, but also we'll be asking for feedback as well, so that we can learn from your experience. How can we improve the machine? How can we support you better? And what science were you able to accomplish on the machine and in the time period, so that we can report that back to the NSF to be able to let them know this is a platform that we can accomplish science on. So here's just a target timeline for we were awarded in 2019 on October 1st. We've already accepted XRAC proposals and awarded allocation time on the machine that was supposed to start October 1st. We will be keeping Bridges 1 running until we put Bridges 2 into production. So we'll be helping to support the community still with Bridges, with the original Bridges, until we can get Bridges 2 into production. We sent out emails to the PIs to let them know that. We'll be working right now on delivery, installation, initial testing, and we'll be announcing the early user program when we're able to solidify the timeline, and then we'll put Bridges 2 into production and move all the data and users over to Bridges 2 and start getting science done with it. So we're really excited about that as well. So this is just the leadership team. I would list everyone that works on Bridges, but I can't make a slide that, well, I could, but it would have to be like a slide that includes the whole PSC. So none of these projects happen by just putting computers down and hooking them up with networking. It's all about the people that are behind it. And we have a fantastic staff at the PSC that has 34 years of experience. Actually, we calculated the other day over 1,100 person years of experience deploying state-of-the-art computational research infrastructure. So these are just some of the people that lead the Bridges 2 project. So Ed Hanna is our Associate Director of Operations. I'm the Principal Investigator. Paolo Buitrago is our Associate Director for AI and Big Data, or AI and Data Science. Sergiu Sanielevic, I can never say his last name right, Sanielevic, he'll say it right after me when he introduces himself, is our Associate Director of User Support. Amanda Slimick is a new member of the team. She's our project manager, and Robin Seebeck is our associate director for broader impacts. So just in summary, Bridges was at least in our mind, was a pioneering platform for bringing together AI, high performance computing, and big data into one heterogeneous, flexible architecture. We're building on that success and taking it to the next level with Bridges 2 to be able to support a new, rapidly evolving, convergent, collaborative, data-intensive computational research community. And we plan on having some, being able to support new and exciting ways to interact, well, not new, but exciting and interactive ways to interact with the research computing. And we really encourage you, if you're interested, to sign up for our early user program and be a part of the team, the Bridges 2 team. So thank you very much, and I'll just leave you with this slide that gives you the links to, and you can, if you don't want to write all these down, you can just go to the psc.edu Bridges 2, and that'll have all the links to where you need to go. So thank you very much, and I'd be happy to take any questions you have.
Great, thank you very much, Shawn. I'm looking forward to seeing Bridges 2 be deployed and getting on there. I don't see any questions in the chat, but every speaker deserves a question. So I'm going to ask.
Sure.
With the large memory nodes, so I know PSE, you have a long history of really doing great things in the large memory space. And I see that now your standard nodes are 256 gigabytes. You have a handful of the 512 gigabyte nodes and then the 4 terabyte nodes.
Yep.
So first of all, why did you stop deploying these extremely large memory nodes? These like 8 and 12 terabyte nodes?
Yeah, that's a great question. We looked at the job mix, and 4 gigabytes was, or I'm sorry, 4 gigabytes, 4 terabytes was really sort of the sweet spot. That's where we were seeing the most usage. So we decided to, we decided to deploy as many of those as we could, as opposed to trying to get extreme memory further down. So 4 terabytes was really sort of where we saw the sweet spot of people using the large memory. I mean, on Bridges, we had 3 terabyte and 12 terabyte nodes. And, that's so we opted for, making sure we had the most capacity at the best price performance. And 4 terabytes is really where we saw people utilizing the extreme memory. So that's why we did that.
Hey, great. Thank you, Shawn. I actually have a whole bunch of other questions, but I could follow up with you later. I want to make sure that Sergio has enough time for his presentation. So you can go ahead and stop sharing, and Sergio, whenever you're ready.
Okay.
Okay.
Oh, Shawn, you need. Yeah.
Are you done, Shawn? Okay.
Yep.
Okay. Well, let's see. Where am I? This thing is getting in my way. Okay, share screen. Okay, and now we'll do the trick that Mike told me, which is F11. Does that work?
Yeah, it still looks the same.
It's still what? It's the same?
Yeah, it looks the same. Yeah.
Well, that's the biggest I can get. So, okay, so in a way, Shawn has already set the stage for, at least for the introduction. So one big thing to remember is that whereas Bridges 2 is what they call the Category 1 award for, I guess, capacity computing, like lots of stuff and kind of solid and, I mean, a good, compromise between it works and it's innovative. This one is one of the 3 so far Category 2 awards that NSF has made in their advanced computing infrastructure buildup. And here the idea is, as it says, unlocking interactive AI development for rapidly evolving research. This is, the mission here basically is over a 5-year period to figure out how this pretty, far out, very special purpose, as it were, architecture, solution, specifically designed for AI, and right now I would say AI training, how that can be used, how that can be integrated into research workflows. And in particular, we do want to get to the point where Neocortex is, I mean, it will be integrated from the start, physically speaking, with Bridges 2, but we want to get to the point where there's a ecosystem that ranges from what Bridges 2 can do, for example, a lot of inferencing workloads, and then also, complementarity with simulation, to the things that really require the specialized hardware that our partners at Cerebras provide. And again, the important thing here, this is actually a research collaboration that we have with Cerebras and HPE. The exact configuration that will go into Neocortex has not been attempted by anyone else. So this is kind of in the PSC tradition of serial number 1 stuff. But what's nice about the NSF Category 2 program here is that we actually get time to thoroughly explore with the user community what can and cannot be done on this architecture. And of course, our partners, especially Cerebras, is extremely eager to know that, what kind of things are useful to the much more general user community that we have as an NSF center. So you've just seen this stuff before from Shawn. This is, the explosion in recent years of compute requirements in AI. And this is, again, one that Shawn showed, but we've added one more recent one from June 2020, where the number of parameters has actually gone up to 175 billion. And I hear that there's a GPT-4, which is even more. By the way, there's folks in the audience that know a lot more about AI than I do, specifically Rajani and Julian, and also John Urbanik, I think, is here. So at the end, if it comes to any kind of questions, we'll be, they'll be here and there to help answer. And then afterwards, of course, we can answer any questions that you might send us. But again, the motivation here is that machine learning workflows are, of course, not simple. Even training is not a linear process, but it's a highly interactive, iterative process where there's a lot of experimentation involved. So, there's a lot of parameters to tune. You have to repeat stuff over and over again. So that's why, for example, no lesser a personage than Yannick LeCun, one of the founding fathers of modern machine learning, pointed out that it would be really cool to have specialized, dedicated hardware just for machine learning. And in a sense, of course, I mean, to some extent, some of the tensor capabilities that NVIDIA provides does that, but this is really above and beyond. So there was a startup, Cerebras, that kind of thought about that, and they started thinking about what are the properties of the right compute for DL, and here you see what the conclusions they came to. So it's supposed to be massive. Much of it is just very sparse linear algebra on tensors. So it would be good to design something at the hardware level that is good at that. Then memory, well, wouldn't it be nice for it to be large, high bandwidth, and tightly coupled with the compute? And specifically, doesn't limit utilization to very large batches. And then also that the fabric should be high bandwidth and low latency and fully configurable. So that was, we'll get to Cerebras in a moment, but that is when we thought about these things. We designed this Neocortex solution, which again, the goal here is to vastly shorten the time required for deep learning training, and then in the larger ecosystem, foster the integration of deep learning with scientific workflows, and really, see what this revolutionary hardware can do. Because as LeCun said, if you have more compute, then you can also experiment with new algorithms and really drive theoretical innovation in the space. So we called it Neocortex because that's the newest and coolest area of our brains, and it's deals with cool things that machine learning tries to do, like audio, movement, visual perception, sensor processing. So yeah, we like that name. The resource is going to be two, not one, Cerebra CS1 servers, coupled by, front-ended by an HPE Superdome Flex. Usually, current deployments of CS1 are, first of all, it's just one, but then they're front-ended by like normal clusters. And we think there's a lot to be said for having a very powerful, large memory, really powerful front end to this. And then behind that is going to be the full power of Bridges 2. So there's going to be quite a lot of storage on the system itself. And then behind that, we're going to have the, again, we're going to have the Bridges 2 file system that's going to be federated. The use cases we were thinking of, demanding deep learning training once again, and then complementarity with the workflows on Bridges 2. Examples we have in mind is, of course, medical imaging. Again, as Shawn said, there's a lot of that BSC and our partners work on. And then also having simulation runs on Bridges 2, and also surrogate models for simulation that can be trained on Neocortex itself. So here are some ideas, and the proof is actually, as I will really dwell on, we're trying to actually work with the user community and see what actually works. But these were, the ideas that we and our partners had that would be good. So here's a block diagram of the system. So we have these two CS1s, and they talk very fast with each other, and also with the Superdome Flex front end. 32, that's 32 CPUs on that thing. And then we go over into Bridges 2 and its file system. So how am I doing on time? Okay. So, and again, all of that is, you can, if you go to the Neocortex website, Neocortex at BSC, you'll find links to all kinds of, discussions and about that. It's also been like an HPC wire recently and things like that. But here's the CS1 server, and it's it's based on the wafer scale engine processor, which is the largest chip ever built. That's a real size image close next to a baseball ball. So you can see it's really macroscopic. And so that's integrated into this chassis. I think probably the first deployment outside of the manufacturer was at Argonne National Lab. They've been running that for a while now. I think there's deployment at Livermore National Lab now, and also I believe at GlaxoSmithKline in the pharmaceutical space. And I think they have some pretty good sales actually going on. So again, largest chip ever built, a lot of transistors, a lot of memory bandwidth. Pretty power efficient, tensor cooled, and yeah, so here's more about the compute. Again, in the interest of memory, I'll just scan through that. And by the way, I left the slides. I sent Bob the slides, so they'll be posted. But yeah, these are some cool facts. You know, the memory is integrated with the compute. All memory is local. The fabric is, you know, is really designed to eliminate communication bottlenecks. So one of the cool things you can do, you can actually not just do data parallelism in training, but you can actually do model parallel training very easily. So there's a lot of interesting features, and yeah, our mission is to kind of explore what that means for real workflows, scientific workflows. Then the HPE SuperDome Flex is very powerful in its own right, and it can do the traditional things like just front-ending, you know, the data, getting the data into the or to the CS1s, but it can do very powerful data pre-processing, and it can also do graph analytics on its own. I mean, you can, you know, it's and what we would like to do at some point is then, I mean, like initially, you know, there's going to be one job, I think, running on each CS1, at least in the early user period, in the, you know, first months. But at some point, we would like to have workflows that scale across both CS1s and also do multi-user, you know, the capability of having multiple users on a CS1. Yeah, it's a pretty powerful combination in terms of how you get stuff to the jobs running on the CS1. Right now, you can bring, you know, your TensorFlow workload and pretty soon PyTorch. And so you just, in fact, there's a whole lot of things that you can already do just on a CPU. I mean, we've done stuff on bridges already where, you know, you use TensorFlow. You can, you know, bring your TensorFlow project, and you can basically see how it maps onto the CS1 fabrics, and you get a prediction on how it's going to, how well it's going to utilize the fabric, and you can get to iterate with your model parameters and things, even, you know, experimenting on your CPU as you compile things, and then pretty quickly evaluate, essentially going, you know, through TensorFlow, evaluate how it's going to perform. And so we will use that in the early user program. This is currently ongoing already in its preliminary stages, which consists in just, so, you know, similar to what Shawn talked about on Bridges 2, early user program is actually a reserved term in NSF speak. So in its strictest manifestation, it'll be a 30 user, at least 30-day hands-on, you know, exercise by some user groups where they will actually run on the Neocortex system once we have it deployed here, and that'll be part of the acceptance. But we have begun to work with users already in terms of figuring out, you know, what their plans are and how they would use the system. And part of it will go, you know, the vanguard in the early user program, but the people who will start in the early user program will then continue on. So what we've done so far is we've used EasyChair actually, because this is not yet an Exceed allocated resource. So we just used EasyChair. We invited proposals. We got 42 proposals in a wide variety of areas here. And now what we're doing, and with Rajani, for example, Paula, and and the Cerebras folks, we're interviewing the most promising of these proposers to see, like, how do we get started? How can we continue? Kind of lay out the roadmap, starting with the first 30 days, but then continuing on kind of in more complex ways as we go into the project. And actually, I'll get to that in a second, but many of us who are working on this are actually ECSS members, and specifically we leverage ECSS NIP to, talk to the users and develop these use cases. So as ever, we are grateful to Exceed and ECSS for that. Here's what the timeline kind of looks like right now. So the project formally started on June 1st. We started taking applications for the early user program in September, during the month of September. And we're working very hard to get the system delivered. As like everybody else, we're working through certain delays and COVID stuff and so on, but we do hope to have it by the end of November, maybe early December, have the system going and be able to start the hands-on part of the early user program and do the acceptance testing. And then based on what we learn and, we continue to talk to people about potential use cases, hopefully including folks who are here. And then we'll just go from there. So this is maybe the most important slide. Get in touch with us. The magic, here are the two magic, the magic website and the magic email. And we hope to hear from you guys and see if we can develop some use cases for you or the users you work with. So here's the summary. This is a very experimental system trying to explore a highly innovative technology. And so we want to see what this thing can do for our user community that we have in Exceed right now, and then going forward to whatever comes next. Please contact us, and here's the team, and I've asterisked all the folks who are actually also part of ECSS. So that's all I had. Thank you very much.
Great, thank you, Sergio. I am really looking forward to seeing this system coming online also and becoming more widely available. Along those lines, so Amit Chirazia has a couple of questions. So Amit, yes. Do you want to go ahead and unmute?
Oh, let me try that. Sergio, thanks for sharing this. I'm curious, is there anyone who is kind of building software, or at least the base software, besides the vendor? And are you guys thinking of doing some software sharing agreement with ANL and Lawrence Livermore, who
I think right. So on the so I briefly in the interest of time, I scooted over a lot of this, but yeah, I mean, there is, of course, the ingestion of existing frameworks, but there's also a language like a C++ API called Lair that people can use to, do their own programming. So that will be opened up to developers. As far as other users, yeah, we're actually talking to ANL and to Livermore about forming like a user group, same as there's, AMD user groups and, things like that. So yes, I think we want to have a Cerebras user group that we're going to be setting up. And again, Cerebras, I mean, the reason that they were very interested in working with us and frankly giving us, a good deal that fit into the pretty narrow constraints of this, phase 2 or category 2 budget, was that they are very interested as a research partnership in working with our community, which is a bit different from the DOE community, as we know, but that's why they were really, really interested, and they are. And so far, our experience working with them has been just amazing, in terms of, so we are very optimistic that as much as, their competitive pressures allow, they will, open up to working not just with us, but with our user community. And, I think, that's definitely part of the plan.
Okay, and Amit, you also had a second question there.
Yeah, so I had another question is that I didn't see in your timeline whether, Neocortex will become available as an exceed allocated system, sometime in future.
It has to. I think they say by year 3 or something.
Right.
Same as Voyager or Okami, but we'll do it as soon as possible. So once we kind of get our bearings and figure out, and like I said, we have about 42, just from the initial dipping into the pool, we got 42 extremely interesting proposals. Some of them are kind of might take some time to, become feasible, but we're looking for more. So, once we kind of work, maybe, so as soon as we figure out that how exactly this fits into the larger picture, and the other part is, how do you even do accounting on these things and things like that. So there's homework that we have to do, both as operators and with the user community. But as soon as we can, we will open up.
Yeah, thank you. I want to say that not only the system looks impressive, but your timeline is also very impressive. So, I look forward to, this being absorbed in the national CI.
And again, and I'll, I guess, reiterate this with my ECSS and NIP hat on, but I think we are actively looking like users that you guys work with as ECSS people and as, research software engineers and campus champions and CARC people, just close the loop with us, and we'll, we want to, the first step is to have a dialogue with the community and kind of see what they want to do, and then do the impedance matching, keeping in mind maybe also the larger ecosystem of Bridges 2 and Voyager, and Expanse has GPU nodes and things like that. So in a holistic way, kind of explore, how we can best use this thing.
Great, thank you, Sergio. So we are a little late. It's 11:06, so I'm going to cut things off here. I don't see any more questions. Again, so Sergio and Shawn, thank you for the excellent presentations. Congratulations again to PSC for winning these 2 awards. And with that, I'll let you go. We'll have the slides and the recordings posted on the ECSS Symposium page soon, and see you all again in December.
Thank you very much.
Thank you very much. Thanks, everybody, for letting us present.